Okay, good morning. Sorry about the length of the video yesterday. I'm going to try to keep this one a little bit shorter, but today we're going to shore up the rest of 3.9. We're going to continue with our derivative of exponential functions, and we're going to get into logarithms. And as I start out here, I have a couple review problems, and all I want to do is, because it went so fast yesterday, is I want to say, remember from yesterday here, the derivative of e to the u, where u is a function of x, the derivative of e to the u is e to the u, but then we have to multiply that basically times the derivative of the exponent, and the way the book writes it is e to the u times du dx, okay? This is the exact same thing as u prime. So it's the exact same exponential function you're looking at times the derivative of its exponent is the derivative of a logarithm, or not a log, a base e exponential function. So let's look at this one. So when I'm looking at y equals e to the raised to the negative x over 4, well, y prime is going to equal e to the negative x divided by 4, okay, because it's the same thing back. Now I got to remember what's the derivative of my exponent, and we want to picture this as this to see that it's going to be negative 1/4, and that's why I left that little spot in the middle. So there's the derivative of that one. And I threw one more on here just for a quick little product rule, and neither one of these are on your note sheet if you're looking for it. So I'm going to think of this as my u times v for my product rule, and remember what I'm looking for the derivative of the first times the second plus the derivative of the second times the first, okay? So y prime equals, well, the derivative of 3x is 3x squared times e to the x squared, because that's times my second term, plus the derivative of my second term here, well, that's going to be e to the x squared times the derivative of its exponent times x cubed, okay? So then, as I'm looking here, this is going to clean up just a little bit, okay? E to the x squared plus, these are going to get put together for a 2x to the 4th, e to the x squared. And I can clean that up a little bit, meaning I can factor out an x squared and an e to the x squared. So my end result, I would like to look at in factored form as x squared e to the x squared times 3 plus 2x squared, okay? And there would be my derivative of that dirty little bugger, okay? And we're going to move right into derivative of other bases, okay? Other bases meaning not base e exponential functions. How do I take the derivative of those? Well, in order for me to find the derivative of those, I'm going to kind of recall one of my inverse properties where e to the ln x equals x. Well, what that really means is, oh boy. What that really means is I realize I'm stretching here, but if I had e, that's an ugly color. If I really had, I don't know, let's say e to the ln 3, what does that equal? It equals 3, okay? And if I really stretched it, and if I said e to the ln of dogs, okay, that's going to equal dogs. Bottom line, e raised to an ln, these things, they go away, and it just equals what's up there. So in order to find the derivative of a to the x, I'm going to be using this inverse property right here, okay? And what I mean by that is for me to rewrite, I want to think of another way. I want to think of another way to think about a to the x, because I don't know how to take that derivative, but I do know how to take the derivative of an e to the x, okay? So we are going to redefine that, And, well, if e to the ln dogs equals dogs, a to the x, well, heck, that's got to equal e to the ln a to the x, okay? So that's just using one of my inverse properties there. And to get that, okay, so what I'm going to do is I'm going to say, hey, these two are the same thing. So what I'm going to do is I'm going to take the derivative of both of them, okay? And that just takes me right down to here. And I have a double equal sign because I don't know what the derivative of a to the x is. But whatever the derivative of e to the ln a to the x is, has to be the same thing, all right? So let's move it along here. So I do not know the derivative here, but I know how to take the derivative of a base e, okay? That is e to the ln a to the x times the derivative of the exponent. Okay, now I got to think of this exponent. My exponent is ln a raised to the x. And we have these logarithmic properties that say, hey, this actually equals x times ln a. Okay, because I can power that down. Well, what is a? Well, let's look back here. A is a constant. A is a number greater than 0. It's just not 1. So what is the derivative of that ln a? It's just a number times x. So if I was taking the derivative of any rogue number 2 times x, hey, that derivative would just be 2 now, wouldn't it? Okay? And I shouldn't cross it off because it is. So I need to picture as I'm taking this derivative, okay, I want to use my property of a log, and I want to see that exponent as x to the ln a, because when I take the derivative of that, it's a linear thing in the top, so it's just times ln a. All right, so what do we get? Well, that's what we get. And as I continue to move along here, okay, well, e to the ln a to the x times ln a, well, what does this actually equal? Well, we came back here in the beginning and we said e to the ln x, hey, that's the same as a to the x. So this is just an a raised to the x times ln a. And that is what the derivative of a raised to the x is, okay? All it is it's the same exponential function I'm looking at, and then it's times the natural log of the base. Example, if I was taking the derivative of 3 to the x power, the derivative of that is going to be 3 to the x times the natural log of the base. It's going to be ln 3, or 3 to the x times ln 3. And if you're like, whoa, Kruger, this is really breaking the rules, because here in my e to the x, if I'm taking the derivative of that, why aren't I taking the natural log of the base? Because we just don't have to do it. So think about this. E to the x is e to the x times the ln of e. What is the ln of e? Well, the ln of e is 1 times e to the x. So the derivative of e to the x, that's why it's just e to the x, because when I take the derivative of the base, ooh, that's a natural log, it just goes away. The ln of e, hey, it's gone. So it's the same. So let's move it on. Because more often than not, that exponent, guess what? It's a function of x. So how do I take that derivative? Well, check it out. The derivative of a to the u is a to the u times the natural log of whatever number that base is times the derivative of the exponent when it's bigger than x, right? A couple examples here. We just did one like this. Well, y prime equals, well, the derivative is going to be 8x times ln 8. And if you don't like writing it like that, okay, you write it y prime equals 8 to the x times the natural log of 8. And I don't need, because this derivative up here, that's just the exponent of x. It's really times by a chain rule of 1, but because it's 1, I do not need it there. And that would be my derivative. Okay? Notice in the next one. The next one, there's a skosh more than just an x in there. So y prime is the derivative of any exponential function is the exponential function you're looking at times the ln of its base times the derivative of its exponent. And there's really no way to clean that up. I mean, I can try to call it, and oh, I want to write all my constants and stuff in the front. Okay, so it's 2 ln 3 times x, okay, times 3 to the x squared. And I know I just kind of got that x written in there funky, but it's just long, and it makes just as much sense here as it does compressed right here. All right? So, what is it? Derivative of exponential equals, it's the exponential times ln base times d dx of exponent. Okay? And that's how I think about it. And I just look at it. So when it was down here, it was 3 to the x squared. My derivative of that is the same thing times the ln of the base, like I said before, times chain rule derivative of the exponent. Munger. There it is. Okay? I will tell you, you're doing all this because you might run into 1 or 2 common exponentials that are non-base e. Most of your stuff on the AP test will be a base e exponential function. All right? So, what does it mean? How the heck do I get the derivative of a natural log? Well, if y equals ln x, then what the heck is the derivative of a natural log? Well, in order to get that, let's change the form of that. Well, if I change the form of that, changed form is e to the y equals x, isn't it? And if I took the derivative of that, I'm going to find the derivative of that logarithm as an exponential. Okay? It's just going to be in terms of y. So what do? Well, the derivative of e to the y is e to the y times, I don't have to ln the e because that's going to turn to 1, but I do need dy dx because I do need to take the derivative of the exponent, and the derivative of x with respect to x is 1. So, what does that mean? That takes me to dy dx actually equals 1 divided by e to the y. I don't want my derivative in terms of y in this case because we're going to be taking lots of derivatives of natural logs. What the heck does e to the y actually equal? Oh, e to the y equals an x. So dy dx equals 1 over x. So that means when I'm taking the derivative of a log, then y prime equals 1 over x. And that's it. Okay? And again, of course, we're going to look at the chain rule. You guessed it. That's just when my log is just x. Sometimes that's an ln. Sometimes that's an ln as a function of something bigger, or an ln of x squared minus 8x plus 3. Okay? Sometimes that is not just x. So when that's not just x, of course there's a chain rule involved. Okay? So as I'm coming along here, basically, now I'll just come straight into the chain rule here. The chain rule, when this is a function of x, the derivative of my natural log, if you notice back here, when I took the derivative, kind of like when I took the derivative of my inverse functions, my inverse trig functions, there was no trig function involved. When I take the derivative of my logarithm, I don't have a log involved anymore. It's gone. It's just a fraction, 1 over x. So I always think of this as the derivative of ln x. Well, it's 1 over x. And oh, Captain Obvious, right? Well, I think of it like that because when u is a function of x, I think of this as 1 over whatever my argument is times du dx. Okay, that's the derivative of my argument right there. So the way I like to look at it is d dx of the ln u, how I used to teach it, is the derivative of the argument divided by the argument. It's u prime over u is another way to see that. That's exactly what this means because that is u prime. What do you mean? You're really walking around everything here. Well, let's hit it. Let's hit an example. So the derivative of, y prime of the ln of x is going to equal 1 over x cubed times the derivative of the argument. Ooh, check it out. What happens there? Oh, that turns into a 3x squared over x cubed. Holy smokes, I can reduce that. That's 3 over x. Whoa, how did you get that? Well, if it's just a simple argument up here, I can redefine my function a skosh too. I can say y equals 3 times ln x if I want, and then I can just use the constant multiple rule and say my derivative equals 3 times 1 over x, which is 3 over x, okay? To be honest with you, a lot of times I don't do that. I just come right up to here in the top one, and I say my derivative of my log is 1 over whatever my argument is times the derivative of my argument, and I squish them together to here, and then I simplify them for my happy spot of the answer, okay? Moving along. What is this one? Again, see now here I can't power rule that out because I have x squared plus 1. I have a sum in there. Yeah, I couldn't even expand this because it's not a product. What is y prime? Y prime equals 1 over the argument times the derivative of the argument. Okay? So that gets me to 2x over x squared plus 1. There is my derivative. Okay? To be completely honest, I usually look and say y prime equals, and as I look at it, I'm like, okay, taking the derivative of u in the top, and I'm putting everything else downstairs in the bottom, so I can shorthand some work out for myself is what I do. Okay, hopefully that makes a little sense. Well, how about the ln of the cosine x? Well, as I'm moving along, okay, thinking of the same thing. Y prime equals, if I went the other way, it's 1 over cosine x times the derivative of that cosine x. Hey, that's a negative sine x, which that's over 1. So that really equals negative sine x over cosine x. And there's a much simpler way to write a sine over a cosine. That would be a negative tangent x. That would be the derivative of the ln of cosine x. Okay, again, it's kind of a little bit work there. So when I usually would write it, I would think of y prime equals derivative of the argument, negative sine x, over the argument, cosine x, of negative tangent x. And I get the same thing no matter how you slice it or you dice it, okay? And from there, what happens if it is not a natural log? Well, it's not a big deal because I know how. If I know the derivative of the natural log of x, if I know that equals 1 over x, all right? What I have is I can change the base of any log into a natural log by taking the natural log of the argument and dividing it by the natural log of the base, all right? Well, check it out. A was always a number in the base of the log because it was something raised to a power, which means this is 1 over ln A times ln x, because this is just a number because A is a number. Well, heck, if I'm doing that, and I haven't taken the derivative yet, by the way, I haven't done this, I'm still redefining my function, okay? So then I would be thinking of this natural log as what is the derivative of 1 over ln A, which is a constant, times ln x. Oh, well, that's pretty easy. It's the constant, there's my times the derivative of ln x. Oh, what is that? It's 1 over x. So my derivative, d dx, if you want to memorize log base A of x, if I took that derivative, what is it? It's 1 over ln A times x. So it's 1 over x, it's 1 over the derivative of the argument times 1 over the natural log of the A, okay? Anytime I do one of these logs, I always change their base to here, and I never forget where does my natural log of my base go. It goes in the denominator. However, of course, the argument, yeah, it might be a function of x. So what does that mean? Well, that means it's going to be 1 over the argument times the natural log of the base of the log times the derivative of the argument, okay? I like to think of this, again, as u prime over u times ln of whatever my base is. Well, let's hammer out an example. Hey, this is base 10. It's common log. If I followed this, okay, I could follow this and I could say, oh boy, all right, well, here's my argument. And I can come, and I really got to think about it, to be honest, because I have 1 over e to the x times the ln of my 10, because that's my base, and times the derivative of my e to the x is still my e to the x. Would that fall out that way? Or am I losing my scruples? Which is over 1, which is going to be e to the x over ln 10 times e to the x. Oh, those go away. In this case, it would be 1 over ln 10. Why? Well, because I can change that base really easy. It's just an exponential function, okay? It's not the way I would do it. Why'd you do it that way? Because I'm trying to follow the formula that a lot of people like to memorize. But if it were me, guys, I would always take this non-base, this non-natural log, and I would redefine this as the ln of the argument over the ln of the base. Oh, because the ln of e to the x, well, that's just x over ln 10. Well, that's really just a constant times x. So y prime would just be 1 over ln 10. And that's why that one went away, because I actually have that base e written inside of it there, okay? And let's see what else we got here. We should have a couple more examples. So how I would recommend you do this, personal preference, I would redefine this as the ln of x squared divided by the ln of 3. I would change that base so that it's really y equals 1 over ln 3, which is my constant, times my ln of x squared. Okay? Then I would differentiate it. Y prime equals, hey, my constant, 1 over ln 3, times the derivative of this. Oh, it's 2x over x squared. I can see these, that's going to reduce. I could have power ruled that 2 out, broke that straight down, but I'm really looking at 2 over ln 3 times x is my derivative of that one. or 2 over x times ln 3. Doesn't matter how you write it. As long as you show you're multiplying, okay, as long as you don't lose that x inside your log, you're okay. You're okay. All right? So I realize that's cruising and bruising through fast. We have one final problem here. It's a little application problem. It's actually a problem that is on page 179. It's number 52. And the spread of flu in a certain school is modeled by this equation. Well, I don't know if you remember what this looks like, what these equations look like, but this is that cute little logistic model you guys used last year for your Starbucks labs or whatever. Okay, remember your logistics typically kind of look like that, where we have a ceiling population and a bottom, and the virus comes in and it spreads, and it's going to peak out until everybody's infected. It's kind of like current days with the Rona. Okay, we can kind of apply this. P is the number of people infected after T days. Okay, this is not going to take us very long to get through this. Estimate the initial number of students infected. Well, if P of T, P is the number of people infected after T days, well, the initial number, wouldn't that be who was infected at time 0 or day 1? And that's going to equal 200 over 1 plus e to the 5 minus t. Oh, really? You're going to make me take 200 and divide it by 1 plus e to the 5th because I'm putting a 0 in there? No, I'm not. That's why it's a cute little calculator problem. Okay, so all we're going to do is we're going to dial up the old CAS here. We're going to graph that little bugger, and I'm going to say menu. I want a graph, number 2. And in that graph, I want a fancy fraction of 200. Whoa, why didn't it give me my 2? My 200 over, what is it? It's 1 plus E. Oh boy, escape. So I need my fancy fraction, 200 over 1 plus E. And what's raised to the E? Well, that's 5 minus, and I can't put a T in function mode. I got to put an X, and we're going to graph that. Oh, I can't see everything. Well, we need to dial this in, okay? And if you remember, that top one was like your carrying capacity. That's how many people are. That's like the population of the school. So we're going to change our windows. I like to change them all at the same time, personally. And we're just going to go from like -2. We're going to go before the virus hit to about 10 days out. I'm going to make my scale 1. And I know my minimum, okay, technically my minimum should be 0, right? But I just like to see my x-axis, so I'm going to go -10. My maximum should technically be about 200, so I'm just going to go a little higher than that. I'm going to go like 220 people. And I don't know, what do I want to put this at? Maybe 20? Who knows? Doesn't matter. Enter, enter, and then I can see my curve there pretty nice. And really, the nice thing is if it's a calculator active, all I need to do to find out how many people were infected on day 1 is all I have to do is come here and I'm going to go menu. I'm going to trace my graph. Trace the graph, and where do I want to trace it? I want to trace it at 0. And check it out, about 1.33857 people are infected. Well, if we're talking about the initial number of students infected, right, can we have a decimal of a student? No, I hope not, because I hope there aren't pieces and parts of students walking around. So then I would say, oh, this is approximately equal to 1 student. And I'm calling, I shouldn't even call them students, I should call them people, because there's actually teachers and custodial staff and aides, everybody in here. We can all get sick, okay? And we have been, okay? Next one, what is it? how fast is the flu spreading after 4 days? How fast? How fast? Doesn't that sound like a rate of change? Okay? Doesn't that sound like a rate of change? How fast is it moving? What's the velocity at which this virus is moving? Well, that's really making me figure out what the heck is P prime of 4. Okay? I could come back and I could algebraically find this derivative, but I don't want to do that because it's a calculator active problem. Therefore, I'm going to come back to my calculator, and not to sound like I'm being lazy, but a big part of the AP exam is for you to know how to utilize your technology. So we're going to say menu. We want to analyze that graph maybe. And what do we want to find out? We want to find a number 6 here, a dy dx. We want to know the derivative at what position? We want to know it at position 4. 39.3224 students per day, because it's a rate of change. Okay? So I would come back, and hopefully I'm going to come here. I'm going to say, I'm going to give it the approximately equal to, okay, 39.3224. Oh yeah, we don't want to do that. We want to say about 39 students per day, okay, because it's spreading at about 39 students per day at day 4, okay? And it's not 39 students are infected, it's spread. There's 39 new students infected, okay? And when the heck will this flu spread at its maximum rate? What is that rate? Well, let's take a little gandy-wandy at our graph, okay? Well, let's pull that little squirrel back up here. When is it spreading at its greatest rate? Well, I wish. Can I? Can I take that? Oh boy. Come on, baby. Let me grab that point and move that point. I don't want to multi-select. Hey, yeah, okay, so I can move it. Now it's getting smaller, and I can drag that derivative. This is finding the slopes. Whoa. I thought I saw a tap. So somewhere, nope, now it's small. It's somewhere right in there. What the heck is that spot in there? Oh, yeah. That's my point of inflection. Can my calculator find that? Because as you look, remember, okay, your tangent lines, it's spreading faster, it's spreading faster, it's spreading fastest, and then it's not spreading as fast. Okay? Oh boy. I lost my upper limit here. I could change that, 220. Boom. And it throws my line off, but you can see how that happens. You know, it spreads faster. So we want to find when's it fastest? Oh, right there at its point of inflection. So let's analyze that graph. Let's find number 5, inflection. Lower bound, all we're going to do is we're going to say, oh, somewhere to the left of where we know it is, upper bound somewhere to the right, and it's going to drop that point for you, okay? And what is it? Well, the point is 5 days in. It's going to spread at its maximum rate 5 days in, okay? And what is the greatest spread rate? 100 people per day. When will the flu spread at its maximum rate? Well, day 5. What is that rate? 100 students per day, roughly. Okay? That's what it's going to spread. And after that, okay, and I mean, I can find that in there, and that's just the oh, wait a minute, whoa. Screwed up there, Kruger. Day 5, there's not 100 students, my God. They're maximize that all out. Let's go back here. Let's go back to our graph and let's read that graph properly, Kruger. So I'm going to come back. There is my point of inflection, yes. That means there's 100 students infected on day 5. But what is my rate of spread? Oh, that's my derivative at 5. That's coming back here and analyzing my number 6, my derivative at position 5, 50. Okay, it's spreading at 50 people per day on day 5. Okay, so day 5, that maximum rate is 50 students per day. Okay, so we really found P prime of 5 to equal that for my maximum rates. Okay, I understand you guys might have questions. If you're lost, if you're not, please reach out to me. I might be available tomorrow for some little sessions as you guys watch this and maybe clarify some other stuff. Shoot me a text if you want to hook up on a Google Meet, and I can fire things up and hopefully clarify a few things for you. Other than that, you should be able to do all your homework for this section. Remember, Monday, the plan is to review for a test on Tuesday. All right? Have a great rest of your day, ladies and gentlemen.